Today, we are diving into a really powerful tool that engineers and scientists use all the time, the Laplace transform. Now, I know it sounds kind of complex, but its core idea is actually brilliant. It's all about making really difficult math surprisingly simple. Let's see how it works.
Seriously, what if you could take one of the trickiest parts of calculus, I'm talking about differential equations, and just turn them into straightforward algebra problems, the kind you could solve with stuff you learned back in high school? Well, that's not some kind of math magic. It's exactly what the Laplace transform is designed to do.
So you might be asking, why do we even need a tool like this? Well, the challenge comes from a specific type of problem that pops up absolutely everywhere, from electrical circuits to how a bridge vibrates in the wind. And here it is, the differential equation. You can think of this as the villain of our story. It describes any system where the rate of change depends on where it is right now. And, solving these things directly, especially when you have second derivatives like this, can be a massive headache. It usually requires a whole bunch of complex methods.
But we have a secret weapon. I want you to think of the Laplace transform as a kind of problem-solving machine. You feed the difficult, messy calculus problem into one side, and on the other side, it spits out something much, much easier to handle.
This slide right here, this is basically our entire game plan. We start over on the left with a hard calculus problem in what we call the time domain, which we represent with a t. The Laplace transform acts like a translator, converting that problem into a nice, clean algebra problem in the Laplace domain, represented by S. Once we're there, we solve the easy algebra, and then we just translate the answer back. It's that simple.
Okay, so how does this magic machine actually work? What's the secret?
Well, the entire engine is powered by one brilliant and incredibly useful formula. Let's check it out. And this is it. This is the engine. The transform of a derivative, that f prime of t on the left, becomes s times f of s, which is just the transformed version of our original function, minus f of 0, which is simply the starting value of our system. This little formula is the key to everything. So why is this such a game changer? For two huge reasons. First, it literally turns the calculus operation of differentiation into simple multiplication by s. That's the trick right there. And second, it automatically bakes the system's starting point, that initial condition, right into the equation. That combination makes it the absolute perfect tool for solving what we call initial value problems. And what's really cool is how the pattern just continues. For a second derivative, we just get s squared. And look at that. It includes both the initial value and the initial rate of change. This same idea works for third derivatives, fourth derivatives, you name it, which makes it an incredibly powerful and consistent tool. All right, enough theory. Let's actually see this thing in action. We're going to watch it take down a real differential equation, step by step. The process is always these same three steps. It's like a recipe. First, we transform the entire equation, getting it out of the time domain and into the s domain. Second, we use basic algebra to solve for our function, which we call y of s. And third, we invert the transform to bring our solution back into the real world, the time domain. Okay, here's our mission. We've got to solve this initial value problem. We have a first-order differential equation, and we're told that our starting point, y at time 0, is 1. So let's fire up the machine. Step 1, transform. We apply our big derivative rule to that y prime, which gives us sy minus our initial value of 1. The transform of y is just y. Then, the transform of the stuff on the right side is something you can just look up in a standard table, which gives us negative 4 over s plus 1. And just like that, poof, the calculus is gone. Step 2, solve. And now, it's literally just an algebra puzzle. We group the y terms together, we move the 1 over to the other side, and we solve for y of s. No derivatives, no integrals, we're just rearranging terms. It's so much cleaner and more direct. And for the final step, we invert. To get back to the time domain, we use a technique called partial fractions to break that result into simpler pieces. Each of those simple pieces has a known inverse transform we can just look up in a table. We put them together, and there it is, our final solution for y of t. Mission accomplished, and we completely bypassed all the hard calculus. So let's just pause for a second and appreciate what just happened. We took what could have been a pretty tricky calculus problem and we solved it using a straightforward, repeatable, purely algebraic process. That's pretty amazing. If you remember only one thing from all of this, let it be this right here. This is the big idea, the absolute heart of the Laplace transform. It converts the hard operation of calculus, differentiation, into the easy operation of algebra, multiplication. It's a simple idea, but it's incredibly powerful. So at the end of the day, we found a way to tame derivatives, to make them manageable. And that opens up a whole world of possibilities for analyzing all sorts of complex systems. Which leads to a really interesting question, doesn't it? What other huge, complicated problems are out there that are just waiting for the right change in perspective to become simple?